Welcome to this third session in the ninth section of the first module of my course on fundamentals of electrical engineering. This module is, of course, electrical circuits, and the section is on two-port networks. And today we move into the interconnection of two ports. Okay, the interconnections of two ports afford a lot of simplification of circuits. We always learn about the block diagram picture of understanding any system. In this case, now we can split up the system into either series connections or parallel connections or even cascade connections, such that each block can be addressed separately, can be interpreted separately, analyzed separately, and then can be put together. So in this context, it becomes important to see the three important interconnections that are going to help us to solve big systems with perhaps these kinds of interconnections. The essential requirement is that we diagnose between the, or we discriminate between the three, or we try to understand what is what. Like for instance, in the first interconnection, which is called as a series interconnection, I hope it's very clear that the two ports are acting independently with respect to each other. What is happening is that when current I1 enters the first network, okay, it could be anything, it could be even a T network or a pi network, okay, and even more complex kind of things. And then if it exits and then enters another network, okay, let's call it as N dash, and then goes back, okay. So, and the same thing is repeated on both sides, that both on port 1 and port 2, then we have what is called as a series connection. If this is the case, then both the networks can be analyzed separately in terms of the Z parameters, or represented separately in terms of the Z parameters. And then just like what happens in a series circuit, because the current is entering one network and thereafter another network and then going back, you can have the Z parameters as combinations of each of these elements, that is Z11 plus Z11 dash, Z12 plus Z12 dash, or Z, okay, and so on and so forth. Okay, so each block in the 2x2 matrix or each cell can be added together separately, and you can analyze them in a you can analyze them separately, and this is something that makes the analysis simpler. On the other hand, if a current splits into two, not equal, need not be equal, if the current on entry splits into two and enters two networks, okay, and then again exits from both the networks and then joins together, as is shown in the second connection, we have what is called as a parallel connection. So this is what we have to do. We have to interpret we have to analyze the manner in which the current enters and leaves on both ports. Okay, so on the first port as also on the second port, if this happens together, if this happens simultaneously, or in other words, the current enters after splitting together. After splitting, it enters two networks, N1 and N2, and then they exit again from N1 and N2 and then join together. Whatever had split earlier now joins together on both ports. Then we are having what is called as a parallel connection. A different and more useful kind of connection and more possible connection happens to be what is called as a cascade connection. In this case, what happens is that whatever comes out from the first network is applicable as the input to the next network. Okay, so then we are having what is called as a cascade connection, and when we are having a cascade connection, the overall T parameters or ABCD parameters is given by the multiplication of the two matrices that represent both the networks separately in terms of in terms of ABCD parameters. So ABCD is the same as equal to A dash, B dash, C dash, D dash, which is the first which is the ABCD parameters of the first network, post multiplied by A dash, B dash, A double dash, B double dash, C double dash, and D double dash being the ABCD parameters of the second network. Okay, I forgot to talk about the parallel connection. Parallel connection, as is very clear, we see that we are having the admittances connected together because we are having a parallel setup there. So the total Y will be given by Y1 dash plus Y11 dash plus Y11 double dash. In the first cell. In the second cell, it would be Y12 dash plus Y12 double dash, and in the third cell, it would be Y21 dash plus Y21 double dash, and the fourth cell would have Y22 dash plus Y22 double dash. Okay, so essentially what we must do would be to diagnose what kind of interconnection is there, and thereafter write out the parameters for both networks separately, then add if it is Z parameters for series connection, again add if it is Y parameters for parallel connection, and multiply the two matrices together if it's going to be the cascade connection. Okay, so the problem number 1 is not essentially something like this, but there's an interconnection, and that's why it's placed in this particular session. So in this section, we see that the two-port network, as was mentioned in the very first one, is a result of some measurements being done. Okay, so we are having A1 and V1 on port 1 and a 6 volt supply energizing the whole system. There's a two-port network in between, and we also have scope for energizing on the second port also, which is equal to which is by 1.5 volt voltage source, and then we are having both current and voltage measurements on the other side. So I1 is measured, V1 is measured, I2 is measured, V2 is measured. E1 is supposedly energizing the system, and E2 is also energizing the system. Okay, so now let's read the problem. Okay, we are having switching such that such that you can do them separately. All the switching can be, all the ports can be switched on separately. Okay, so a two-port network shown in figure is shown below is excited by external DC sources. The voltages and currents are measured with voltmeters V1, V2 and ammeters A1, A2. All that we saw earlier, all seem to be ideal as indicated. Under following switching conditions, the readings obtained are. So we are having S1 open. So when we are having S1 open, it means I1 is equal to 0. Okay, and that is reflected in ammeter A1 is equal to 0. So I1 is equal to 0. What does it mean? Okay, but of course S2 is closed as it has to be. Otherwise, it would be isolated kind of system. Okay. At that time, V1 was measured as equal to 4.5 volts. So this is something to do with the energization on the second port. Okay, and V2, okay, which is the voltage which is connected to the 1.5 volt source as it is, and that's equal to 1.5 volts. Okay. And then A2, that is I2 is equal to 1 ampere. Okay, so in this first case, we are having a situation wherein I1 is where I1 is equal to 0, and so we are having parameters described accordingly. Okay, and then when you are in the second case, when S1 is closed, okay, so now 6 volt is made applicable, and at the same time when S2 is open, 1.5 volt is isolated from the circuit. Now A1 is equal to 4 amps, I1 is equal to 4 amps. Okay, and V1 is equal to 6 volt, and V2 is measured as equal to again 6 volt, and A2 is equal to 0. Of course, A2 is 0 because we have isolated the source from there. Okay, so I2 is equal to 0. Okay, so there are two conditions, and the requirement is that we find out the Z parameters. So obviously, when we are having Z parameters, we first write out the equations. So what are the equations? V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 I2. Okay, so this has to be remembered. Okay, now let's start thinking in terms of, let's say I2 is equal to 0. So when is I2 is equal to 0? That's for case 2. Okay, so in case 2, we see that we are having when I2 is equal to 0, we can find out Z11 as V1 by I1. So just take case 2 and then just take V1, which is equal to 6 volt, and what is I1? I1 is read as equal to 4, so 6 by 4 is equal to 1.5. So easily you can, so long as you identify the different cases and separate them out, you can easily do them. Okay, and now what we want, when I2 is equal to 0, we can also find out Z21 as V2 by I1. Okay, so Z21 is equal to V2, and what is V2 when I2 is equal to 0? It is V2 is equal to 6 volt, and what is I1? I1 is equal to 4 amps, so 6 by 4 again is equal to 1.5. Okay, very easily you can do it, and that's though the problem looks a little complex, okay, but because of so much of English and a diagram, etc., this is one of the easiest problems to do. Okay, so moving on, and you will get 2 marks as well. Okay, so moving on to the case when I1 is equal to 0, that's case number 1. So I1 is equal to 0, and when I1 is equal to 0, you can get Z12. What is that? V1 by I2. So V1 by I2 is 4.5 divided by 1, that is 4.5. Okay, and what else do you get when I1 is equal to 0? You get also Z22 as V2 by I2. Okay, so what is V2 then? V2 is equal to 1.5, and I2 is equal to again 1, so 1.5 by 1. Okay, So very simply, you can write out the Z parameters. So Z parameters, so now accordingly, you see that option C is appropriately containing all the contents of Z11, Z12, Z21 and Z22. Okay, okay, so that's right. And then we move on to the next part of the question, which actually gets you more marks. That is H parameters matrix for this network. Okay, so from Z parameter representation, you can actually you can use the equations and derive. Otherwise, you can do it directly. I prefer do it directly, because you're first writing out again what is what with respect to the H parameters. So V1 and I2 are expressed as V1 is equal to H11 I1 plus H12 V2, and I2 is equal to H21 I1 plus H22 V2. Okay, so now we look at the two equations that we have already derived, wherein we see that we already have V2 is as equal to 1.5 I1 plus 1.5 I2 from the Z parameter situation. Okay, so from there you isolate out I2. So I2 is now the same as equal to dividing throughout by 1.5. So we are having 2 by 3 V2 minus I1. Okay, and then we write out again V1. Okay, from the earlier equation, because that is what is going to remain steady. Okay, the second equation has to be manipulated, and the first equation can remain as it is. What is V1? V1 is equal to Z11 I1, so 1.5 I1 plus Z12 I2, so 4.5 I2. Okay, so now we already know what is I2, so substitute for I2 is equal to 2 by 3 V2 minus I1, and so you get an equation. From there you can separate out the different contents, and you can see that we are having H11 as equal to minus 3, H12 as equal to 3, H21 as equal to minus 1, and H22 as equal to 0.67. Okay, so very easily you can find out the different H parameters values just by manipulating the second equation from the Z parameters and substituting in the first equation in the Z parameters, and just reorganizing such that the same appearances held true. Okay, I hope this is clear and it's easy, and this is the pattern that we have to continuously follow when we are given a particular parameters and we have to get the other one. Write out the parameters, write out both the parameters, go for the second equation, reorganize it such that you get one quantity, okay, and then substitute in the other, and then you are done. Okay. So moving on to the third problem, where it's a cascade arrangement, okay, and two passive two-port networks are connected in cascade as shown in the figure. Voltage source is connected at port 1, okay, so V1 is connected, and then it is made available at port 2, okay. Of course, it is made available through the two cascades, okay, and of course we know that V1 and I1 as in ABCD parameters, as also V2 and I2 will be given by A1 V1, B1 I2, C1 V2, D1 I2, and then A2 V3, B2 I3, and that's V2, and I2 is equal to C2 V3 plus D2 I3. Okay. Moreover, we realize that I2 though is I2 and V2 happen to be on the on port 2 of network 1, they also are shared by the second network as the first port. Okay. And that's the reason why when you are having the multiplication of two cascaded arrangements, you see that ABCD is now equal to AAAB or A1 A2 plus B1 C2. Okay, so of course this is just a row and column wise multiplication, and the result is given there. Okay, so I've zeroed it on two aspects because of what is going to be asked. Okay, so A1 B1 C1 D1 A2 B2 C2 D2 are the generalized circuit constants. If the Thevenin's equivalent circuit at port 3, so now we have to look at the system from port 3. Okay, but we apply the voltage at V1. Okay. Consists of a voltage source Vt and an impedance Zt. So that's the Thevenin's equivalent connected in series. Then of course in the Thevenin's equivalent they are connected in series. But the application of voltage happens to be in V1. So this V1 voltage has to go until up to the port 3. So how do you do that? You realize that you will get from the understanding that V1 by V2 is what. Okay. So then in this case it's going to be V3, that's all. Okay, so that will give you VT. Okay, so it's obviously we know that the connection is established using AAAB plus BACB. So, or in other words, we realize that VT is the same as equal to, okay, or is the same as equal to V1 by, because this is V3 multiplied by so much is equal to V1. So, VT is the same as equal to V1 divided by the first cell in the combination, that's equal to A1, A2 plus B1 C2. Okay, so that's clear. So that's VT. Now what about ZT? Okay, ZT, we see that we can get the short circuited current and this voltage. Okay, take the ratio, that gives us Thevenin's equivalence. So when you short circuit, you realize that you are having a connection between the established connection is now going to be the same as equal to, of course there is there are two cells. One is of course what we had, the voltage is already estimated as V1 divided by A1 A2 plus B1 C2. Now this has to be now divided by the current magnification, and that's given by the cell B. Okay, cell B is given by AA, that is A1 B1 plus B1 D2. Okay, so that comes on the numerator because it's a division, and so it's very simply you can see that ZT is this, ZT is equal to Z1 is the same as equal to the multiplication is there. Okay, so I suppose answer D is correct with some mistakes. Okay, but still I suppose that's okay. Okay, fourth question is very simple. The two-port networks are connected in cascade. Okay, as we saw right now, the combination is to be represented as a single two-port network. The parameters of the network are obtained by multiplying the individual matrices of ABCD parameter matrix. Okay, that's what we were talking about so far. Okay. Now again we are having a circuit where two circuits are shown to be in cascade because two blocks are there. In the first circuit we have only one series element, that's Z1 angle, Z1 with 10 angle 30 degrees as the impedance, and Z2 is seems to be an unknown value. Let's read the problem. Two networks are connected in cascade as shown in figure. With the usual notations, the equivalent ABC and D constants are obtained given that C is equal to, okay, C is given as equal to, that is the totality, the total C, okay, is given by 0.025 angle 45. The value of Z2 is, okay, so the first thing that we have to write out again as usual is what will be the connectivity with respect to the ABCD parameters. So V1 and I1 are given by AV2 minus BI2 and I1 is equal to CV2 minus DI2. Okay, so if that is the case, then we realize that C is the ratio between V2 and I1. Okay, the output voltage divided by I1. Okay, so it's very clear that we are having C as I1 by V2 and I1 creates a drop. So I1 into Z2 is equal to V2. Okay, when I2 is equal to 0. Okay, and that is given as equal to 0.025. So what is the value for Z2 is very simple because we see that we see that just that reciprocal is enough, or in other words you can take the take the reciprocal of 0.025 angle 45 degrees. So you are having minus 45 and 1 by 0.025 is the same as equal to 40. Okay, so this is the way that you can do this particular problem. Okay, I hope it is clear. Though I have done it in the detailed manner as well, separating them out as two ABCD parameters, and it's shown here wherein we see that C1, okay, we have that combination C1A2 D1 C2 as equal to the total C, which is equal to 0.025 angle 45 degrees as is given, and this is when I1 by V2 this is equal to I1 by V2 when I2 is equal to 0. Okay, here C1 is equal to 1. You can see that, okay, because of the sparseness in terms of elements here. So C1 is equal to 1, A2 is equal to 1, D1 is equal to 1, and C2 is equal to 1 by Z2. Okay, so 1 by Z2. So C2 is already given as equal to. So C2 is the only content and it's given as equal to 0.025. Just take its reciprocal, you get what is called as 40 angle minus 45. Okay, so very simple. So long as you understand both the methods. Okay, one is seeing them as one single block, or seeing them as being in cascade. Okay, in the sixth problem, two two-port networks are connected in parallel. Okay, obviously when you are having parallel, you have to think in terms of the Y parameters. The combination is to be represented as a single two-port network. The parameters of this network are obtained by addition of the individual Y parameters. There's no doubt about it. Okay, so we come to the last problem in this session. That is the seventh one. Okay, and there are two cascaded networks. Okay, one has all 3 ohms. Okay, no, not cascaded, I'm sorry. So we can see that the current splits. Okay, and the current splits and goes into the 3 ohm network, and then it returns, okay, from the baseline of the 3 ohm network, the pi network made of 3. Okay, and then similarly the current again also moves into the right at terminal 1 of port 1 dash. It moves into both the both pi networks. One is 3 ohm one, the other is 2 ohm one. There also it moves in there, and then from both the networks via the baseline they come back and then join together to go back to 1 dash. Okay, the same thing is repeated at port 2, where 2 is the exit point, okay, coming from both 3 and 2 from the top terminal, and then again from the bottom terminal, from the bottom line they both merge into 2 dash. So we are having a parallel connection. Okay, so when you are having a parallel connection, to get the combination, it's very clear that we need to go for what is called and what is asked. Let's see the H parameter model of the 2-port network given in figure. The value of S22. So we need to find out S22 of the combination. So we start with Y parameters, and then as was mentioned earlier, we work on the second equation and we substitute in the first equation and we are ready. Okay, so let's work on pi parameters. Let's work on Y parameters using the pi network. So if it's the pi network, then each of these impedances now need to be in the admittance form. So they are all 1 by 3. Okay, similarly the other one is also having a pi network with half ohm as half mho as the admittance, okay, or half Siemens as the admittance. Okay, so now let's compute y11, y12, etc. Okay, so based on this, so what is and we can write out the total y parameters. So what is the total? Okay, so that's the reason why first y parameters, the h parameters are written, and then y parameters are written, and then you add them together. Okay, so we are writing out the circuit with 3 ohms or 1 by 3 mhos for the y parameters. So what we have here, 1 by 3 plus 1 by 3, that's equal to 2 by 3 forms y12. Okay, y11, y12 will be the common with a negative sign, which is equal to minus 1 by 3. Okay, and then again, which is the same for y21 minus 1 by 3 from the pi network. Okay, and then we also have 1 by 3 plus 1 by 3, 2 by 3 as y22 for the network with 3 ohms as in the pi network. Okay, when we move to the pi network with 2 ohms, now it is going to be half plus half 1 as y11 in this case. Okay, and then we also, the same is applicable for y22 also, and then y12 and y21 are the same with minus half. Okay, so that's all done. Okay, now we want to have them in parallel. So now we are having the combined circuit with again the y parameters as given by the equations for y parameters as given by I1. Okay, plus equal to y11 plus y11 dash being the quotient of V1. Okay, so what is that? 2 by 3 plus 1, that's equal to 5 by 3. Okay, so similarly we'll see that this is applicable for 2 by 3 plus 1, and so this is the same for y22 also, but it will come in the subsequent equation. Okay, and now we also want to have the next coefficient for V2, which will be minus 1 by 3 plus minus 1 by 2, which is equal to minus 5 by 6. Okay, so that's okay. And now from here V1 has been separated out. Why V1 has been separated out? Because if you look at the H parameter equation, we are happy to retain V2. Okay, if you look at the H parameter equation, I1 is equal to y11 V1 plus y12 V2. So V2 is okay, but V1 has to be replaced. Okay? So that's the reason why V1 is separated out, and we see that V1 is equal to 3 by 5 I1 plus half V2. Okay, from the just made equation. Okay, and I2, of course, we are going back to the y parameter representation of the combination. So I2 is equal to, again we add minus 1 by 3 to minus 1 by 2. So it's again minus 5 by 6. As it is, they were common, and this, as was mentioned earlier, Z11 and Z22 happen to be the same and equal to. Okay, you can also combine. It's the same. If they are different, you had better combine. So it's going to be 5 by 3 V2. Okay, so now what do we substitute for? We substitute for V1 from the just obtained material. So we put it there, and we see that's the same is equal to 3 by 5 I1 plus half V2. Okay, and I2 is equal to minus half I1 plus 5 by 4 V2, and this we compare with I2 is equal to H21 I1 plus H22 I2. So it's obviously H2 is the same as equal to 5 by 4, which is equal to 1.25. Okay, so I suppose the steps are very clear. What is okay, so since the parameters are given in a network manner, which is parallel, first we have to compute the Y parameters, okay, and then the combinations we need to add together. We have used several things that we have done earlier, that is the pi network, okay, how it can be utilized, how we have to work with admittance, etc., and then you add them together to get the total admittance parameters. Okay, now we are ready for the H parameters. So you write out again the H parameters, and you see that in the first equation itself, okay, of course we are interested more in the second equation, so we need work only with the second equation, because only what is asked is H22. Okay, so we have to get what is called as in this particular format. I2 is equal to H21 I1 plus H22. We have to get it in this particular format, and so you just do a few manipulations. That's all that's required. Of course, you'll have to work with pen and paper. That's the major difference with for two-port networks as such. That is, you have to work a little with pen and paper. Otherwise, you might make mistakes. But be as systematic as is possible, as organized as is possible, such that you are right. Okay. So I suppose today's session was also clear, and perhaps there are too many concepts, but still be clear that when you are having a cascaded arrangement, okay, you can go for it directly, okay, based on what you know about it. Especially only ABCD parameters were asked, so you can get the total ABCD parameters directly, okay? Or you can use the cascade arrangement. Okay, again, please notice that in this case, because of the sparsity of the system, you are having C1, A2, and D1 as equal to 1, only C2 is equal to 1 by Z2, as was mentioned earlier. Okay, and then you are having ABCD parameters, and you have to take and then since the Thevenin's impedance is seen from the output terminals, okay, so you have to work back from the first from the applied voltage until up to the time that you reach here. Okay, and Z2 also, Thevenin's also is connected in series with it. So whatever was available, whatever was applicable earlier, that is V1 by I1, has now got to be promoted until up to it reaches the last two port. Okay, yeah, so switching in, switching off, etc. You can again I repeat that you can retain the same thing, either same theme all through. If I1 is equal to 0, everything that is associated with I1 is equal to 0, and if I2 is equal to 0, everything that is associated with I2 is 0. Okay, similarly V1 and V2, etc., as the case may be. Okay, so I repeat that actually the interconnections of networks lessen the difficulty of understanding, as also applying, as also analyzing, and implementing huge circuits, because we can think in terms of subcircuits. Okay, so we go to the next session in the last session, and with that we conclude two-port networks. Thank you.